Welcome back to our videos about systems of linear equations. Before we investigate the issue of solving systems of linear equations, let's first have a look at some simple examples, see how these actually look like, how the solutions could look like, and also how to get some geometric interpretation for these simple two-dimensional IUs here. So this section contains a couple of examples on systems of linear equations. We'll start with this system of linear equations here, x1 minus 3x2 equals 9, and 2x1 plus x2 equals 4. Of course, we want to solve this equation system, and there is a number of ways you can do this. Again, we'll learn about a systematic way later on, but let's just try and solve this more or less intuitively. What we could do is we could solve, for example, the first equation for one of the variables, let's say x1. That seems particularly easy. So, equation 1, I'll usually use Roman numerals to enumerate the equations here. So solve equation 1 for x1. We're doing this. Well, this is equation 1 again. We're solving this for x1. We get x1 equals 9 plus 3x2. Add 3x2 on both sides of the equation. And the second step would then be to plug this into the second equation. Second equation is 2x1 plus x2 equals 4. And that means if we plug in this relation here, x1 equals 9 plus 3x2, what we get is 2 times 9 plus 3x2 plus x2 equals 4. Now we have an equation that only contains one variable anymore. So we can try and solve this. Let's see, this is 18 plus 6 x2 plus x2 equals 4. So let's take the 18 to the right-hand side and add 6 and 1 x2. So we get 7 x2 on the left-hand side. We get minus 14 on the right-hand side. So the solution for this is x2 equals minus 2. And of course, from this, we can just use back substitution. So we can take the result that we got here from x2, plug that into the first equation, and then compute x1. So we use back substitution to compute x1. Remember, we solved for x1 already. Here, x1 is 9 plus 3x2. So with x2 being minus 2, we get 9 plus 3 times minus 2, or 9 minus 6, or 3. So that yields our solution space. Call that S. That is one tuple where x1, the first coordinate of our tuple, is 3, and x2 is minus 2. Just write it in this way. I could also write it horizontally. It doesn't really matter, at least not for now. So this is meant to be x1, x2. And of course, in this simple setting, one can ask, how would that look geometrically? What does that actually mean, this equation system and that solution? If we look at that system once again, you can see these are equations in two variables. That means what you could do is you could solve for one of those. Say, solve for x2 and interpret that as a function of x1. So you could say x2 is a function of x1. Each of these equations is indeed a functional relation. And of course, you could then draw a coordinate system and draw the graphs of these functions. If you do that, you will find you get lines here. And want to have a look at that geometry to see how the lines in this example actually look. So here's the geometry of that case. And you can see this green line here, that corresponds to the equation 2x1 plus x2 equals 4. And the blue line, that corresponds to the equation x1 minus 3x2 equals 9. So all points on one of those lines satisfy one of those equations. And with the equation system, what we're looking for is a point that satisfies both. And of course, that point is located exactly on the intersection here. So that is the unique solution we get. And that exactly has the coordinates 3 for x1 minus 2 for x2, as you can see. So that is how the geometry of this equation system looks like. Now let's have a look at one more example. Let's say modify our system a little. Let's say we have x1 plus 2x2, 4, and 2x1 plus 4x2 equals 8. Again, we want to compute the solution. And to do this, we'll use a different method, just to see that different methods may lead to the same goal here. Let's start by multiplying the first equation by 2. Multiplying equations by constants doesn't change anything, unless you use 0, of course. That zeroes out the equation. That will lose information, so don't do that. But multiplying by anything other than 0 is fine. Multiplying equation 1 by 2 yields the system 2x1 plus 4x2, 8. And the second equation is still 2x1 plus 4x2 equals 8. 1, 2. And of course, if we have several equations in a system, then we can also add or subtract those equations from each other. Right? So if we have a solution for that system, then of course any sum of two equations needs to be satisfied by that solution, and vice versa. So what we can do is we can subtract the first equation, the new first equation, from the second one. So subtract 1 from 2. What do we get? Well, 1 is not changed, so we just write it down once again. And the new second equation will be, well, 2x1 minus 2x1 is 0. 4x2 minus 4x2 is 0, and 8 minus 8 is also 0. So this is an equation that is always true. And that means that second equation doesn't really add any information to the system. everything that satisfies the first equation satisfies all of the equations. So we can just solve the first one. And there's still two variables in there. So let's choose one. Let's choose x1, for example. We call this for x1. And we get x1 equals 4 minus 2x2. And what that means is, for each value of x2 that we may choose, there is a corresponding value of x1, and that is determined by this equation here. And this tuple that we chose arbitrarily, and the x1 that we computed that corresponds to it, that tuple is a valid solution. And every such tuple is a valid solution. So we don't just have one solution, but we have multiple feasible solutions. For each possible value of x2, we obtain a feasible solution of the system by setting x1 in this way. Okay, so what that means is, for each value of x2 in the real numbers, we obtain a feasible solution of the SLE by setting x1 equal to 4 minus 2x2. And what does that mean for our solution space? Well, that means our solution space is determined in the following way. We choose x2 arbitrarily, and we choose x1 to be 4 minus 2x2. And we can do that for every x2 in the real numbers. Okay, so we have an infinite number of solutions, and this is the structure of that solution space. We could also write this down. We'll usually do this later on by separating the constant parts and the x2 dependent parts of that solution space. The constant parts here is 4 in the first coordinate, 4 here. The second one doesn't have a constant part, so we just write 0. And then we write plus x2 times, and that's the x2 dependent part, minus 2 here, and 1 here. Like this. And again, x2 in R. Now this x2, this would be called a free variable, but we get to that in one of the next videos in some more detail. Again, let's have a quick look at the geometry. How does that look like if we interpret the equations as functional relations? Now, again, here's a geometric representation. The blue line here, that corresponds to the equation x1 plus 2x2 equals 4. And of course, also to the other equation, because it basically has the same set of solutions. So that's just this one line that we can actually see here. The solution set, you can also see the solution set here. That is derived in the following way. You have this point 4, 0, that's here, this one. So you basically go to that point, and then you add something. You add a multiple of minus 2, 1. Now minus 2, 1 points in this direction. So 4, 0 plus minus 2, 1, that would give you this point here. Well, then you have this x2 in front of that. So that would be the solution for x2 equals 1. For x2 equals 2, for example, you would get this point plus this vector plus once more. So you will end up here. And of course, you can also use fractional values. So for x2 equals 1/2, for example, get this point here. For negative values, you'll end up somewhere there. So all in all, what you get for the solution set is, geometrically speaking, this whole line here. So that line, that is the solution set S. Okay, so in this case, that solution set is a line. And we later see that this is indeed pretty typical, at least for the two-dimensional case, and there are generalizations for higher dimensions as well. Okay, I have one last example. It looks like this. 3x1 plus 7x2 equals 21. 6x1 plus 14x2 equals 21. Let's try to solve that system. Make it short. So this time, again, I'll multiply the first equation by 2, and what I get is 6x1, 14x2 equals 42. And I'll just copy the second equation. And then I'll subtract equation number 1 from that one. And what that yields is 6x1 plus 14x2 equals 42. The first equation, I'll just copy that. And the second one I get is, well, 6x1 minus 6x1 is 0. 14x2 minus 14x2 is 0. And for the right-hand side, 21 minus 42 is minus 21. So clearly we get 0 is equal to minus 21. And of course that is complete rubbish. So obviously that cannot be true. And to mark things like that cannot obviously be true. We'll use a symbol like this, a lightning bolt. Can never be true. So what does that mean? Well, it means there is no possible solution. Those two equations can never be fulfilled at the same time. Whenever the first one is fulfilled, the second one's not, and vice versa. And what this means is this SLE does not have a feasible solution. Or in other words, the solution space is the empty set. Again, let's have a quick look at the geometry to conclude this video here. So what does that look like? So here we have the geometry of that system of linear equations. Again, we regard each equation as a functional relation. And this line here, this corresponds to equation 3x1 plus 7x2 equals 1. And the second one, that corresponds to 6x1 plus 14x2 equals 21. And what you can see is, again, all points that solve the blue equation lie on the blue line. Okay. All the points that solve the green equation lie on the green line. So if we're looking for a solution that solves both equations simultaneously, looking for a point that lies on both lines simultaneously, and there is no such point. These lines do not cross. So a system like this in two-dimensional space corresponds to two parallel lines. And again, there are similar things in higher dimensions, and we'll talk about this in future videos. Okay, this concludes our little example session here. And in the next videos, again, we'll be concerned with how to solve these and larger systems of linear equations in a more systematic way. I'll see you then.